Hi, Calc2 class. In this video, we continue with working in what are called the comparison tests, and they're in section 11.4 of the book. So we just did the basic comparison test where you compare two series to each other, but you have to know which one is bigger. And sometimes you have a good comparison and you can't tell which one is bigger, or the comparison points the wrong way, so you can't use the basic comparison test. If you're ever in a situation where you can't figure out which one's bigger, but you think that it's a good comparison to have, or you know which one is bigger, but it's the wrong one, then you can do the limit comparison test, and that usually does work. It has the same suppose as the basic comparison test. Limit comparison test asks you to be using positive term series. That's it. But the additional one here is that when you take a limit of the ratio, that you get a number L, and the L can't be 0. If that happens, then either both series converge or both series diverge. So let's take a look at an example. And I'll show you what I mean as something either you can't tell or it points in the wrong direction. All right, so let's do this one. We're going to examine the sum from n equals 2 to infinity of 1 over n to the 4/3 minus n. Now that is a slight change from the one we already did, because we did 1 over n to the 4/3 plus n instead of 1 to the n to the 4/3 minus n. We'd still start out by examining it the same way, that between the two terms in the bottom, this guy's the higher power, so this guy's the dominant term. So if we wanted to compare it to something that's similar to the one we already have, we would hang on to that term. And to make it simpler, we'd ignore the other term. So I'd be comparing it to this one. Okay. If you subtract something away from this value, it makes it smaller. And if the denominator is smaller, that makes the ratio bigger. So the comparison would be like this. And again, that's because this guy has the smaller denominator. Smaller denominator. Okay, this one is a p series, and your p is 4/3, so the p is 4/3, it's greater than 1, so this series converges. Okay, well, if it converges, then that right-hand side there, that's a finite number. And the other one then is greater than or equal to a finite number. Well, you know what's bigger than or equal to a finite number? A larger finite number, or infinity. So it doesn't tell me which of the two cases it is. If it's a larger finite number, it's still convergent. And on the other hand, if it's infinity, then it's divergent. So this comparison is not useful. Basic comparison test didn't work because the inequality pointed the wrong way. Okay, but I still think that I have a good comparison because this is simpler and not that different because it contains the dominant term of the other one. So I'm going to try the limit comparison test instead. Instead of having one that's greater than the other, I'm just going to do a ratio. So you take the limit of the ratio. So let's take the limit of the ratio. The limit of the ratio. Okay. Now, I put, by the way, the theorem here doesn't care which one's on top and which one's on the bottom. So whichever way you write it down is fine. I'm just going to keep doing the algebra. So when you flip that, you'll get n to the 4/3 minus n all over n to the 4/3. And then if you distribute that denominator, you'll get 1 minus 1 over n to the 1/3. Because this is n to the 3/3, and there's a 4/3 here, so there's an extra 1/3 left over. Okay. Cube root of infinity, though, is still infinity, so it's 1 over infinity for here, so it's 1 minus 0, that's 1. And all that counts is that's not 0 or infinity. If you're not 0 or infinity, then either both series converge or both series diverge. I already know that this converges because we already explained why, which means since the one from 2 to infinity of 1 over n to the 4/3 converges, so does the one in question, 1 over n to the 4/3 minus n, by the basic comparison test. Oh, sorry, this was the limit comparison test. So the moral of this story is that if you have what you feel is a good comparison, but the inequality points the wrong way, don't try to do basic comparison test. It won't work. But the same comparison using the limit comparison test is likely to work. All right, let's try another one. All right, so we're going to take a look at this series. And exponential terms, where the base is bigger than 1, they grow faster than polynomial terms. So for example, when the n here is a 6, this is 64, the 2 to the n is a 64, and the n is just a 6. So this gets bigger than that does, which means that this guy's the dominant term. So the thing to do is make a comparison to the one without that in there. Okay. Okay, so this one is the same as the integral from 1 to infinity of 1/2 to the n. And I know what that one does because that's geometric. So this guy converges since it is geometric with the absolute value of r being 1/2, and that's less than 1. So now I know the series converges. I know I have a good comparison. Now let's see if the basic comparison test works. If you subtract something away in the bottom, and it's making the bottom actually smaller, that makes the ratio bigger. So this guy, between the two of them, that one has a smaller denominator. And that means that this guy will be bigger than or equal to the other one. Okay, but this one converges. So this guy's finite. And all this shows is that the series that I am examining is bigger than or equal to a finite number. Well, you know what's bigger than or equal to a finite number? Another finite number. So, for example, whatever number this is, that plus 1 would be bigger, and then that would converge because it would be finite. But another thing that's bigger than a finite number is infinity. So this, just based on this, could be infinity or finite. What that means is the basic comparison test won't work. Even though I think I have a good comparison. So I'm going to try the limit comparison tests instead. All right. The limit comparison test just asks for the ratio, and it actually doesn't matter which one's on the top and which one's in the bottom. So let's take the limit as n goes to infinity of one of them divided by the other one of them. Okay, so let's go oh, 1 over 2 to the n in the top, and the 1 over 2 to the n minus n in the bottom. Okay, and then we'll just do some algebra. So we will flip this guy. So that'll give me a 2 to the n minus n all over 1. 1 to the n is just 1, so this is the same as the limit as n goes to infinity of 2 to the n minus n all over 2 to the n once you distribute that power. Okay, so that's the limit as n goes to infinity of 2 to the n divided by 2 to the n, which is a 1, and then you still have a minus n divided by 2 to the n. I have to figure out what that limit is, though, because it's infinity over infinity form, so I don't actually know what the value turns out to be. But if it's infinity over infinity form, usually the best thing to do is L'Hopital's rule. Which is what I will do in the next video. See you there.